working on is you have a bunch of devices or sensors that generate data or time series. And this is a very generic model for almost any complex system. You can think of these nodes as neurons in the brain, and we measure the neuron activity. And the question then is often in understanding the systems, complex systems, is there an interaction? And in which direction? In which direction is the interaction? And one way to do this is to formulate this as a plain machine learning problem, a linear regression problem. So you would look at a pair. So you study pairs of time series and say, okay, at some fixed time, t0, so these need to be synchronized. You need to know the precise timing of this series. Otherwise, you cannot analyze the time series dependence, of course. You use this as the features x from one time series and try to predict the future of this time series as the label. And then you basically shift, you have a sliding window, then you get a new feature vector and you get a new label, y2. And that's how you build up a data set for linear regression, for example. And as Thomas pointed out, it's typically not enough to say if we can predict the future from the past of this, but what we are actually interested in is, does this past help? Does the past of the other, let's say of node I, this is node I, help in predicting the future of node I prime beyond what we can do already with the past of node I prime? So we somehow want to cancel out or subtract from this analysis the intrinsic correlations of this time series at I prime. So we first try to predict the future of time series at I prime using the past at node I prime, and then we see, can we do better if we add the features from node I, if we add the past from node I? Does this help? Does this reduce the training error? And if yes, then we could say, okay, there might be a dependency in this direction. Node I might drive, so we could say node I drives node I prime.
How are you using, how are you evaluating the performance? Are you using some kind of information criteria or?
No, it's a training error. It's average squared loss, average squared error loss, for example.
Because a priori adding variables shouldn't decrease the loss, so decreasing the loss shouldn't, it's not necessarily an indicator that it's explaining something. If you add more variables, the error should not increase, right? So it's non-decreasing function. So
Yeah, but does it decrease significantly?
well, what's significant?
That's a good question. I would say maybe 10%, 20%. I don't know.
I think if you want to go in this direction, one way to look would be to go is to use information criteria. So like confirmation criteria, but basically the criteria that penalize for the number of additional variables. Because you actually want to see the intrinsic value of adding more variables, right? So if after penalizing for additional variables, your performance still improves, then probably there is added value in adding those variables, versus if it does not improve, versus if the added value is balanced by the number of variables that you added, then maybe by the 10% or whatever number, it's not worth adding those variables.
Yeah, but does this approach not also involve some thresholds that you need to set to declaring, okay, this is now a significant improvement or not?
I don't think so. Let me double check. I mean, I think the basic scenario is that is where it essentially computes your training error, but it penalizes for the number of variables you used.
Yeah, but this you could take into account also by setting the required change in the loss. So if you add more other data sets or more other features, then you need to see more decrease in order to be significant. I mean, I don't see how this fundamentally solves the problem of setting such hyperparameters.
Um,
Uh, I wonder if it would be like valid to compare it to like a longer bit of or a larger bit of the like original times series or a larger window. So
Yeah, the window size is also an important hyperparameter.
yeah, so if the window size there is like if we say it 10 there, and then you add 10 from the other time series,
Yeah.
should it then be compared to a window size of 20 on the original? Because then they're like the size of the features are the same, and
Yeah, I would start with varying this window size. Let's call this window size H, and then plotting the prediction or forecasting error as a function of the window size for a fixed lag into the future. So let's say we want to predict 2 time steps ahead. We fix this, but we vary H. And then at some point you might see that this flattens out. So beyond a certain window length, you do not get more information because it's like a more of a dynamic process. So it doesn't remember over longer periods of time. And I would say once you get into this floor, this is the H max, the maximum window length, and then you continue working with this.
yes.
Yeah, this is then this H max is what you use for comparing against the effect of adding the features from the other data from the other time series.
Yes.
Okay. And yeah, I mean, this is really a simple recipe for turning such a seemingly very difficult problem of estimating dependencies of a complex network into basic machine learning problems. And once you have done this, I mean, it's not too difficult then to change from linear models, so linear predictions, to nonlinear predictions. And then you can study, do you have nonlinear effects? So you would use, instead of the linear model here, a multi-layer perceptron to predict the label from the features.